let's take a look at the cross product, and I want to kind of use an intuitive approach here to understand what the cross product actually gives us in a physical situation. So if you can bear with my lack of artistic skills, I'm going to draw a bolt here. Pretend like that's a bolt. Yeah, okay. In fact, I'm just going to make the bolt a little easier. Yeah, get rid of some of the sides. Okay, and I put a wrench on this thing. So my wrench may look something like this. Give a little dimension to it. There we go. Okay, now, here's the idea. I'm going to take a look at the center of this thing, from the center of the bolt to the end of the wrench. That's how long the arm is, so to speak. And I'm going to, in terms of vectors, I'm going to refer to that as a vector R. Now, if I apply a force to it, let's see, from here I apply a force at some angle. So I'm going to call this my force vector. What happens is I end up, this bolt, let's draw the rest of it. There's the threads. This bolt will start to turn. And it turns as a result of torque. So thinking of this vector coming through here, that I'm going to call tau, the Greek letter tau, and this is going to actually be my torque vector. So I'm going to have a force acting on this wrench, and obviously as long as, well, the longer the wrench is, I'm sure you know from experience, if I have a big long wrench and a rusty bolt, it's easier to pop that thing and get it going than it is a really short wrench. And that has to do with the amount of torque that you're generating from applying this force. So we'll use this idea as a basis to understand what the cross product's actually given us. Now, the magnitude of the torque depends on two things. The first thing is it will depend on the distance from the axis of the bolt. The axis is what I'm referring to right here. It's the axis that goes through the middle of the bolt to the point where the forces apply. And that distance, this vector r, I'm going to say is the magnitude of the vector r. And the other thing that applies is the scalar component of the force of this force vector that is perpendicular. I use a symbol for perpendicular to vector r. Because see, if I'm pulling at an angle, the only component that's gonna move this, I need to write there. Move him up here. See, the only component that's going to make this thing turn is what's perpendicular to r. So this component of the force vector, which would probably be a little bit shorter, but you get the idea. No, that's about right, the way I drew it. This component of the force vector is the only thing that's going to make this wrench turn and result in a torque. Think for a moment, if this force vector went this direction. See, this angle now is 0, and there's no torque because it's pulling. There's no twisting going on. So that perpendicular component, I'm going to say this component, that perpendicular component, see this component, is actually the only component. It's supposed to be an M, that's horrible. The only component that can cause rotation. If we look at this again just a moment, here is my vector r. And let's just say that this is my force vector at some angle here. And I'm going to turn this into a right triangle. With this being theta. So the component that I'm talking about here is going to simply be the magnitude of f times sine of theta. The magnitude of f, the length of f, times sine of theta. That gives me this piece right here, which causes, let me change colors, which would cause, that's perpendicular to r, that would cause rotation. So based on that, I'm going to say the magnitude of the torque is, see, the magnitude of that tau vector, the torque, which is going to be the magnitude of r times the magnitude of f times sine of theta. Now, let's take this a little bit further. If vector n is a unit vector, that points in the direction of the boat, not of, how about direction the bolt is screwed or screwed in, then the torque vector is then going to be tau. This vector is going to equal the magnitude of r, like I did before, times the magnitude of f times sine of theta times n. See, this is a scalar. This component right there is a scalar. So if I multiply that scalar by this unit vector n, I will get a torque vector. This is not a torque vector. This is the magnitude of the torque vector. So if I take the magnitude and multiply it by a unit vector, I will have a vector of this magnitude. And it is exactly this idea that we use to define the cross product. We denote this vector tau as being equal to this vector r cross f. So tau is the cross product of r times f. And that's referred to as the cross product, or sometimes you hear it referred to as simply being the vector product. These are the two ways that you will commonly hear in reference to the cross product. Now let's actually take a look at a little bit more a formal definition here. A cross B, where both A and B are vectors, is equal to the magnitude of A times the magnitude of B, of course these are vectors, times sine theta times n, where theta is the angle between A and B, between 0 and pi, and n is a unit vector. It's perpendicular to both A and B. You notice it is? If I take a look back at my diagram here, let's go back to my wrench. See, n is going to go this direction right here. So when I multiply it by this scalar component right here, then I get this torque vector. So n, if you look at this, is going to be perpendicular to both of these. You think these two are going to reside in the same plane, and this is perpendicular to both of them. Okay, see, A and B are whose direction is defined by the right-hand rule. It's the direction of your thumb when your fingers curl from A into the direction of B. Now, because of this, A cross B is not the same as B cross A. These are actually different. Let's take a look at, see if I have a vector, say, let's put it here. This is vector A, and out here is vector B. If I take a look at A cross B, remember it's the n is a unit vector perpendicular to A and B whose direction is defined by the right-hand rule, the direction of your thumb when your fingers curl from A in the direction of B. So when I put my hand here and on A and curl my fingers curl in this direction with my thumb pointing up. So n, this unit vector n, will come out of the page at us. It's going to come directly toward us. On the other hand, B cross A, the only way I can get my fingers to curl toward A is if I turn my hand essentially upside down. And in that case, this vector n will go into the page. Oh, actually away from us. So even though the magnitudes are the same, the direction of this normal vector will in fact be different. Now, as a direct result of all this, and I kind of mentioned it earlier, a direct result of this definition is the ability to determine if two non-zero vectors are parallel to each other, since their cross product will be 0. Remember the wrench thing? If I have this force vector in this direction, or any parallel force vector, so I have a force vector that's parallel like this, it's not generating any torque. It's not generating a component that's perpendicular to R. So any vector that's parallel will result in a cross product of 0. So here's vector A. Here's vector B. Again, there's no torque if we think of it in terms of torque. So A cross B will always be 0. So if I have two vectors and I check their cross product and I end up with a cross product of 0, that tells me that those two vectors are in fact parallel.